So when you have like a salt would be positives and negatives that are intertwined. So we won't get real too complicated with it, but a salt would have positives and negatives side by side. So this would be like NaCl in the crystal form. Kind of like tic-tac-toe. Okay? And so what happens, water is polar. We know it's polar. Because this side's negative and then this side's positive. So what will happen, a water molecule will come across and we'll go through a process of hydrating the salt. So this negative side here will pick this one up and take it away.
So are the circles and the pluses and minuses, is that another?
The plus would be Na. And the negative would be chlorine. And they're just intertwined. So that'll pull that one off and it will go, and then another water will come in and attach itself to this negative ion and pull it away. It doesn't form a bond, it just pulls it away. Okay? And it just keeps doing that until it gets saturated. We'll talk about this term saturated. But it can't do that forever. It can't just continually make the salt disappear. It gets to a point of where it's like a towel, like our paper towels. They get saturated and they don't wipe up anything, right? There's no absorbance on our paper towels, so you're pushing around water, unless it's a little spill. So that means saturated means it can't hold any more. You're maxed out. And so that's what we'll talk about, saturated here and what that means. But we'll have mixtures that are unsaturated, which means that there's still room for more ions to be distributed through the solution. That's called unsaturated. Saturated means that it is maxed out due to a certain amount of volume of the solvent, and it can't hold anymore. Okay? And that's different for different solids that you're dissolving. Different solids will have different saturation levels that we'll talk about.
So the H2O doesn't connect to the big thing, the little, like, you know how the circle, like on your drawing, it just has the Cl.
Yep, just pulled it off. There might be a Cl off of this one too.
So the H2O doesn't connect to the big, the little?
No.
Okay.
And then, so then sodium might be off of this one, you know, just kind of intertwined throughout, okay, when they pull them apart. So that's kind of the process of what they call hydration. I think hydration, you guys kind of probably understand. Hydration is, if you look on page 364, it kind of shows that process in the upper left-hand corner. Now, one thing you've got to be conscious of, and I think you had some problems that dealt with it, had to do with polar and nonpolar. What do we know about polar and nonpolar substances? What do we know about those? If we put them together, what do we know is going to happen? I just want to ask you guys, since you guys did some reading and some things, if I put those two together, what's it going to look like? The bottom of page 363 should give you some help. It won't mix. It won't mix. They'll be separated out. Okay? They'll be separated out. So like, for example, if I have water here as polar, this is why they don't mix. We've got, let's say, a compound with like CH. Now this is in the gas form, so this is probably not the greatest example, but for this it'll work. This is polar, and this is nonpolar. Okay, so what will happen is these water molecules, they attract one another. Why do they attract one another?
Positive and negative charge.
Yeah, they have partial positive and negative charges, or they have hydrogen bonding also, and so they've got a little bit of pull for one another. Okay, and we call that, what do we call that? Remember what general term we associated with this attraction?
Bond.
Nope.
Hydrogen.
Well, yeah, it could be hydrogen bonding, but what's the overall concept that we talked about in the past? Not covalent. These are covalent here. These dotted lines represent what? Well, they can. I think you're saying dipole, London dispersion forces, hydrogen bonding. They're all under what? No. I starts with an I.
Ionization.
No.
Oh.
Intermolecular
forces.
forces. I know, guys.
That's bad.
Okay, it hadn't been that long ago.
Oh my god.
So, this guy's going to try to fit in here.
He does it though.
Can't. They're not going to let him in. Okay? They say, sorry, you're not like us. You need to go off with your own kind. So, this CH... Now, what makes this CH... What are two things that make this CH4 nonpolar? Tell me.
Charge.
Not charge.
I tried.
What two things make this nonpolar?
Having the 4 around it.
What's that?
Having the 4 around it.
Right. They all cancel out one another, right?
Good job, Ray.
They're tetrahedral. But what else? This carbon is, I think, 2.5, and then hydrogen is like 2.1.
They're electronegativities.
Yeah, they're sharing equally for the most part.
They're not ionic, are they?
Nope, they're not ionic. They're sharing. Anytime I show a line, that means covalent model. So they won't fit in there. Okay? But do you think other polar substances can fit in with other polar substances?
Sure.
Yeah, they do. Because the positives and negatives can intertwine.
So
It's
what
kinda-
made that nonpolar?
What's that?
What made that nonpolar then?
The carbon and hydrogen electronegativity is not much difference. Yeah. So the big thing in chemistry that AP's learning right now, they've got to go back and review some things because they got an AP test that'll be a college level test they're taking on Monday. And they have to know all this stuff. So you guys' recall is important. It's not like you learn it and then you forget it. Okay? And I'm kind of seeing some forgetness here. All right? Of how this works. Okay? So, polar dissolves polar. Nonpolar dissolves nonpolar. They give a little thing that explains this. Like dissolves like. So, if the things are alike, they will mix. If they're unalike in polarity, they won't mix. So, like dissolves like. So, I think you had some problems, didn't you? Dealing with if something would mix or not. Correct? All right. So, let's take a look at your questions. Started out with what? Question number 2? Okay. The answer for question number 2 would be the solute is acetic acid and the solvent's water for A. For B, and we're on page 364, okay, and we're number 2. Water is the solvent and sugar is the solute. C, bromine, Br2 is the solute, and methylene chloride is the solvent. Questions on that? Got them right? Okay. Did we skip over to number 6?
Yeah, sure.
Okay. So number 6, it says water's polar and hexane's nonpolar. We actually did this lab. We actually took, you guys remember where we had to identify something as nonpolar covalent, polar covalent, and ionic, the lab? And we had to try to mix A, B, C, D, and E. And if we mixed it with water, what did it categorize it as, possibly? So if the substance says it mixed with water, this, for example, this would have mixed with water. So what could it have been? Could have been a polar solute, or, because polar dissolves polar, right? Or it could have been what? Ionic, right? If it's ionic, what did it do? It won't dissolve in hexane because this acts like polar. So this would not have dissolved in hexane. Okay, but what did we do to see if it was ionic? Take that next step. Because it could be either polar, covalent, or ionic. So what was the next step we did? We checked the conductivity. And if it conducted electricity, we said it was ionic. If it didn't conduct electricity, we said it was polar. Okay, does that make sense? All right? That's what you guys had to do. You had to write that up. You had to say, hey, this is the reasons why this particular substance is this way. Okay? So we're going to go over some things with the electrolytes here in a second. Let's take a look at the answers you have for 12.6. Okay? Number 6 is insoluble. It didn't dissolve. It shouldn't dissolve. B, shouldn't dissolve. C, dissolves. And D, dissolves. Did you guys have that?
No, we didn't have D.
You guys didn't have to do D?
Yeah, we did. Oh.
There's a D there.
So ionic dissolves too.
Ionic dissolves too.
No, there's not.
Did they misprint your book?
Hey, are we guessing what this is?
I thought you said 12.
12.6.
Oh, I just said, yeah.
Okay, so vegetable is nonpolar. Water's polar. They're not alike. They don't mix. Real simple concept. Nonpolar, oleic acid, is a fat. Doesn't mix. Okay, niacin, vitamin B, mixes. Alright, and iron sulfate mixes. Now there are some solids that don't mix, right?
True.
You guys remember we did the double displacement reactions where we said if these two ions are in proximity with one another, they'll form what? They'll form a bond, right? But if they come together, what will we see in the two solutions? What will it look like?
Like the same thing.
But if I take one of these and one of these ions, I put them together and they don't mix, what will come out? A solid, right? They're insoluble. There are some things that are insoluble, right? We're trying to get you thinking back knowledge, okay? The next one you guys had to do was 8.
Yeah.
NaOH is a strong electrolyte, and CH3OH is a non-electrolyte. How is the solutions of an NaOH different from CH3OH? Well, NaOH forms ions, and those ions will allow electrons to be transferred. And the methanol, that's what CH3OH is, it's a molecule, and it won't form any charged ions, and it does not let anything through. So that segue is what we're going to talk about right now. Okay? So, again, a strong electrolyte you guys have written down is something that ionizes completely, for the most part, forms a lot of ions in solution. A non-electrolyte is one that can dissolve, but it doesn't form any ions in solution. Okay? And then a weak electrolyte, there are some ions that are formed in solution. Okay? So we're going to talk about this thing called solubility. Okay? There's different types of solubility. Solubility, there's a lot of factors that affect it, and it's the ability to dissolve. So there's two that you have down. There's saturated, and then there's unsaturated. And most of you have just basic understanding of saturated and unsaturated already kind of know. the differences you have between the two. Okay? So when you look at those two, for example, saturated is a solution that contains the maximum amount of solute. It's said to be at equilibrium. What that means, we can go ahead and show that here. That would be like NaCl. You've got double arrows, and you got Na plus Cl minus. That means, that double arrow means that it goes back and forth. It gets to a point where if I dissolve some NaCl, the NaCl will get back together and will go back the other direction. So it's kind of at a standstill. All right, I'm going to dissolve some NaCl. Okay, if you're going to do that, I'm going to put some together and it's going to form the original solid. Okay, I'm going to dissolve some more NaCl. Fine, go ahead and do that. I'm going to make some more NaCl solid. And so it gets to the point where it's maxed out. Can't dissolve anymore. Okay?
So
And
those arrows facing both ways?
Yes, they go both ways. So you're having the same amount going both ways. That's what they mean at equilibrium. We won't talk about that. We do that in AP Chemistry. We talk about equilibrium. Constantly talk about that. It's something that kind of looks like the reaction's not going anymore, but it actually is. It's just at equal amounts both ways. An unsaturated solution is a solution that does not contain the maximum amount. Okay? Any questions that you have on that? Okay, I would like you to turn over to page 369. We won't do any problems today. We will do these tomorrow. I thought we'd get to them today, but we'll do them tomorrow. I'm going to give you an assignment. An assignment's going to have some problems in it, and it's going to have some questions with effects of temperature and pressure on solubility. And it'll be due on Thursday, and I'll have you hand it in.
Can we put it in, you want to sing it in?
Yeah. But it won't be due until Thursday. Okay. So, let's talk a little bit about this thing about what types of things affect the solubility. There's a lot of factors that affect solubility. Okay, and we've already talked a little bit about it. So, what's one thing you can already tell me about what affects solubility?
Temperature.
Temperature, what else? We'll get into temperature here because it affects some things a little different than others. But what did I already talk to you about solubility? We just went through it. What types of things can mix, what types of things can't mix? Polar can mix with polar, and nonpolar can mix with nonpolar, right? So that is something that affects solubility. Okay? If they're not alike, they don't mix. Okay? Ionic can dissolve into water. Not everything that's ionic dissolves into water. There's some things that can't because they're too tightly bound together. Okay? So we're going to look at temperature affects solubility. Temperature of the solute. Okay, so you guys could probably tell me. If we increase the temperature of a solvent, how does that affect how much can dissolve? What do you think?
Increases.
Increases for the majority of it, not everything. But if we increase the temperature of the solvent, a solid solubility increases.
So is it a direct relationship?
Yep. Now, you would think it's a direct relationship. I want you guys to look on page 369. Look at all those solids in figure 12.5. They got Ki, glucose, sodium nitrate, potassium nitrate, NaCl, Na3PO4. As the temperature increases, they all have different ways they're affected. And it's not a perfect straight line. A lot of them are curved. So it's not what we would call a predictable, right? A predictable, you double it, then this doubles. It's not that kind of a direct relationship. Okay? All right. So, but if we increase the temperature of a solvent and we relate it to a gas solute will decrease. So, gases you can't dissolve as much. They go down. Look on page 369. I want you to take a look at nitrogen, carbon monoxide, and oxygen. As the temperature goes up, it does the opposite. They all go down. Okay, what's always consistent in the two tables be the dependent variable? What do you see present in both of those that represent solubility? Okay, what is solubility measured in? What's it measured in? On the side, on the y-axis. Grams per what? 100 grams of water. So, if you're going to measure solubility, we're always taking 100 grams of water, and that's what the numbers represent. X number of grams in 100 grams of water. And then you can look at it, if you increase the temperature of the solvent, the solute solubility increases. If you increase the temperature of the solvent, a gas solute solubility would decrease. So the last thing we'll talk about is on page 370 is Henry's Law. Henry's Law. Once you look at Henry's Law, as you look at Henry's Law, I will demonstrate Henry's Law. What's it say about pressure and its effect on solubility? What kind of relationship?
Directly related.
Directly related with what? So the solubility of a gas is directly related to the pressure. So if the pressure would double, how much more can you dissolve at that temperature? Double. Okay, so you guys understand why they have this under pressure, right? Because when you open it up, what happens to the pressure? Releases, and now this is under usually about 4 or 5 times the atmospheric pressure, so you can dissolve how much more CO2? 4 or 5 times the amount of CO2, carbonated. When you leave it unopened for a period of a few hours and you go to drink it, it is flat. Why? Because it's lost all its carbonation. Why? Because it's bubbled all out, because it's not as much pressure. It's not going to stay in there the same as what it was before. So they carbonate drinks to show you that. So I'm going to take a little bit of good old Mountain Dew, pour it in. Now this is I kind of had sitting out. We're going to go ahead and pull out the pressure. So what do you think you'll see happen?
I don't even know.
Well, make a prediction.
It'll get all bubbly.
Okay. Why would it get bubbly?
If it's trying to take it out.
It can't dissolve in much CO2. Right? I don't know if I got a good enough seal there, but we'll find out. I think I do. You see it? Looks like it's boiling, doesn't it? It's not boiling. What is that coming out? CO2. So basically I can get all the CO2 out of there because it's going to go to zero pressure. How much CO2 can be dissolved at zero pressure? Zero. Zero. You can't have any CO2 in there if you don't have any pressure, so it all comes out. Does that make sense? So this is Henry's law.
What does it taste like after you do that?
You want to taste it?
I would.
You can taste it. I let everybody know.
Oh, look, the floor you
So CO2's been taken out. You want to taste her?
You want to let me eat the marshmallows, please?
Yeah.
What does it taste like?
Is
It's
it-
like, just flat, like it's super, I don't know how to describe it, it's like.
Just kinda like sugar water.
Yeah,
With some flavoring of Mountain Dew.
yeah.
Okay? So now they used to have these things called fizz keepers, and I think the premise was really good. But what gas has to be above here has to be CO2. So it has to be pressurized with just CO2 gas. If I pressurize it with nitrogen gas, the air, and oxygen gas, and put more pressure above it, guess what? I'm not going to be able to dissolve more of CO2. Okay. All right. So tomorrow we'll look at the problems based upon solubility.
I'm not gonna write down
It's the most like yeah. If you take me what
Yeah, that's why
same. Yep.
I slept in that class.
He didn't really like
Dude, is he good dude with the mustache?
I think he has.
In glasses. I drove with
It's gonna be this
Mm-hmm.
I drove with Mr.
it.
Dude, every single time we go.
Take what?
Looks, man, looks.
Dude.
Yeah, we'll figure it out. Maybe Thursday.
I drove so nicely. I was the first one.
No, he's so low, so as long as you don't go over like.
You better not fail.
I knew I was driving safe or something.
Yeah, take it in Fairbury or
This
one.
girl,
I put right
Well,
here and I passed it.
for me,
I don't think it's really that
the
far.
dude always.
I passed it the
for-
second
He said
time
if we
because
can go 1 mile an hour.
Did he turn the wrong way?
Or we can go 10
What?
mile an hour under.
I'm not
so
very-
so
Gosh,
we went
it's
1 mile
very
under,
good.
we can slam on the brakes. Super.
Dude, I was like, I asked my sister, like, when I see this, like, do I
Having all
turn the
those
radio on? Do I, like, turn it off?
I had it like barely.